Thank you. Yes, I hope you will not only understand but grow to love them, as I have. Yeah, as mentioned, there was a sort of break between working in England and going to Portugal. So there was many reasons for that, but it certainly gave me the opportunity to leave my old work behind and concentrate on something entirely new, which was suggested to me by a fellow I'd met at Warwick, who was from the States as well, and he'd just taken up a position there at Warwick to do numerical simulations of the of turbulence, and he had just finished a postdoc at Infer with in Jim McWilliams' group, and all he could talk about was doing something on the atmosphere, trying to find out what the energy cascade was like in the atmosphere, and that there had been some recent results, some recent theory, and recent reanalysis of the data by, not the same data, but different aircraft data from Nastrom and Gage, who have these classical spectrum k to the minus 5/3 and k to the minus 3 spectra in the atmosphere, which is probably in all the textbooks these days. So he said, there's a new data set, QuickScat. It's just coming out. He says, how about doing some of that? And I said, well, why not? I'm looking for something new to do. I always wanted to get involved in some geophysical fluid dynamics. I just have to learn some geophysical fluid dynamics. Oh, and I also had to learn something about turbulence and what the heck structure functions were, and how to deal with scatterometer winds, scatterometer data. So all that was new to me then, and I thought, it'd take me 2 years to get up to scratch. 10 years later, the paper finally came out. So hopefully no one else will have to go through that kind of pain. Let's see. Oh, just to introduce my colleagues, Jur Vogelzang and Odd Stoffelen at KNMI in the Netherlands. They are the ones, so I'll be talking about not just QuickScat, but ASCAT, a comparison of the QuickScat and ASCAT data. I'll tell you all about those things. Ad Stoffelen is the head of the KNMI scatterometry group, and the PhD supervisor of my group leader there in Barcelona. And he's the main man for developing the ASCAT data set, ASCAT winds. Okay, so we're going to be working on the atmospheric mesoscales, going from 20 to 2,000 kilometers. And for, as you know in oceanography, flows thin in one direction, rotating rapidly, or have strong density variations. The turbulence is going to be quasi-two-dimensional. In the atmosphere, there are also some three-dimensional effects that perturb all that. So let me just also add, I've just given this talk to a physics department, so I was tailoring it to, I was told there that I was going to have a group of biophysics people, so I had to try to explain what all these things were. So if I belabor a few things that are very obvious to you, I apologize. Okay, so yeah, let me just go back. Okay, so one of the key things, whoops, there we go, is the mesoscale convective systems. That gives you a little picture of what those are, and that will come up again a couple times in the talk. Okay, sort of off the screen a little bit, but there's been an ongoing debate in the turbulence community since the 1960s about whether or not atmospheric kinetic energy is transferred downscale, like in three-dimensional turbulence, going from large eddies to small eddies, or upscale as in 2D turbulence, where you have the constraint of vortex, you can't stretch, you're constrained to have the vortices in the vortices in the vorticity in the vertical direction. So you can't break up those eddies, and so instead you go from small eddies to large eddies. That's the basic picture. So which way is it? Which way does nature have it? And the question is of what interest. When I arrived in the States last week, I arrived at Dallas-Fort Worth Airport, and the immigration guy said, "You've been away from the country a long time. What are you doing here?" And I told him, so I've worked on atmospheric turbulence. I'm going to make some visits, talk to some people about things like that. And he says, atmospheric turbulence, climate, what interest is that to society? It was Texas, you have to understand. So I quickly tried to educate him. Okay, so one of the answers is that it has implications for the predictability of weather and climate. I didn't mention climate to him. But weather he appreciated. And of course, very important for tracking of hurricanes to determine where they make landfall, as we saw with Hurricane Sandy. Okay, a little bit about the process of measuring winds. We don't measure winds directly. We infer the wind speed and wind direction from backscattered radiation. So the basic scattering theory involves scattering off the ocean surface, and we're doing Bragg scattering, where the incoming radiation is in resonance with short waves. The facets are normal to the incident radiation, will give you specular reflection. And the fundamental assumption is that small-scale waves are in equilibrium with the rain. So that's the basic framework for the scattering theory. And the backscatter is a function of wind speed and incidence angle. This gives you an idea of that dependence. And since it's sensitive to wind direction, okay, and it's modulated by surface roughness. Okay, so here's a little picture of a very low wind situation, incoming radiation, the blue arrow, giving you basically a complete reflection, so you get no backscattered radiation. Then as wind starts to pick up, you start to get some backscatter. More wind, more waves, stronger backscatter, and then the really meaty stuff. And it's always amazing when you see things like that. Okay, so the quick scatterometer, well, I say the quick scatterometer, it's actually the sea winds scatterometer on the QuickScat satellite, but everybody just calls it QuickScat winds, and so forth. So that went up in 1999, and it's still up there, but will eventually be coming down in a controlled manner. But the radar dish on the scatterometer stopped spinning in November of 2009. So that was taken off duty for collecting winds. We have this rotating dish, and it's sweeping a circle as it's moving along the track, and with inner beam and outer beams and polarizations and so forth, all important in the scattering information. And it gives you these very nice wide swaths, about 1,800 kilometers wide. So it gives you a very nice picture. So meteorologists love this. It operates in Q band, about 13.4 gigahertz. It has a complicated scattering geometry to pick out the wind vector cells, as we call it, to try to bend the radiation and bend the resulting wind vectors. And the most awful of all is that the wind vectors are degraded by rain. So when you have heavy rain, the radiation is just scattering off the rain. You don't see anything. And that means that in the heavy rain area, the heavy rain areas are, of course, in the tropics. So in the big convergence zone. So you have a lot of missing data. So you have to deal with all this missing data, and the corruption it causes even when you still have enough to retrieve, it can still cause some artifacts in the retrieve and muck up your data analysis. But in the higher winds, even though there's rain up here, it's not as heavy. The wind is stronger, so it doesn't affect the data nearly so much in the higher latitudes. The other instrument is the ASCAT. It's got a fixed antenna array. It has a nadir gap, so a blind spot in between. So you have these sort of thin ribbons. So that's not as useful for seeing the larger structures, but on the other hand, it has a simple geometry, so it's much simpler to get robust estimates of the wind and wind direction. Most important of all, it's unaffected by rain. So at these frequencies, it doesn't see the rain. Okay, to produce a wind speed and wind direction, one develops a empirical geophysical model function that relates the ocean surface wind speed and direction to the backscatter cross-section measurements, written functionally like that. All these parameters I've already mentioned. And in order to get the wave speed and wind direction, you have to invert that GMF, which is a very ill-conditioned problem. Lots of nasty things in there, nonlinearities, noise, etc. And in the end, what you get out of it is a situation where you have multiple solutions called ambiguities, and you have to have some criteria in which to select the best one, select the most physical one. And the QuickScat produced by JPL uses called a median filter, sort of an engineering solution, which is quite good. It's an adaptation of a technique used in image processing. There are some problems with that, but still it's pretty good. And the one at KNMI uses a spatial sort of meteorological consistency, shall we say. So it has some other nice physical aspects to it which make it a bit more pleasing to use. Okay. All right. Now, what do you get out of it? Here's some example of some power spectra, energy spectra. Here I'm just going to show it for the ASCAT winds. So you get a spectra, energy spectra as a function of spatial wave number. And what they have packaged, because in order to choose the wind direction, they have to get the whole algorithm started. So they use a ECMWF forecast model to get the algorithm started. And so they packaged that information also in with the data set, interpolated to the same spatial positions and spatial times as the scatterometer data. And for the ASCAT, that's been ECMWF, and for the JPL QuickScat data, that was INSEP. It's probably going to change, or maybe it's changed, or maybe it's going to change soon. I don't know exactly the status. But for the European product, it's ECMWF. So here's two spectra for the zonal wind and the meridional wind in taking data from the along track direction. And you can see the blue is what we measure, and the red is the numerical forecast model. And all this bit in between is what the weather prediction model misses out. So we are seeing more small-scale structure in the scatterometer than the forecast wind. And you can also see in the ASCAT a little bit of difference between the two directions. There's a little bit steeper curve here, and then it starts to flatten out. The flattening could be a little bit of noise, probably a little bit due to a bit of noise at these high wave numbers. And the steepening, well, there was some, turns out it was a management decision to do some extra filtering of the data on board the spacecraft, on the scatterometer. And so we cannot reprocess the data without this extra filtering to see if we could straighten those things out. But in the new, there's a new ASCAT, METOP B. This is from METOP A satellite. The scatterometer on the METOP B, which has been up for a couple of years now, following the other one, does allow us to go back and re-examine the data for these regions. Okay, now this is the region of the world where where I did my work here that I'll be talking about. So is this the tropical Pacific? How does everybody learn about this in all the oceanography? So stop me and tell me to move on more quickly if you want me to. Okay, so this is sea surface temperatures for the month of August, average for the month of August, with the quickscat winds, monthly averaged wind in the white arrows. We have the East Pacific warm pool, the intertropical convergence zone. This coming out here is the South Pacific convergence zone, and the monsoon trough region, where genesis of a typhoon genesis region. And I took this region between, say, minus 10 south and 10 north, divided it up into these 9 boxes. Large box along the equatorial waveguide, and the smaller boxes on either side. And for the comparison, there's an overlap period between the quickscat and ASCAT instruments between November 2008 and October 2009. So we can look at how things vary over the seasons as well as cross instrument. So these latitude time plots, monthly and zonally averaged for each of these 4 regions, I've indicated in these horizontal dashed white lines. That's the equatorial box in there. And then, so the sea surface temperature, you can see the warm pool oscillating back and forth with the season. This is the El Nino 3.4 region. You can see it oscillating as well. And this is the cold tongue region of the cold tongue. And you can see that there's a bit of convergence. Warmer sea surface temperatures enter the region between March and June. There's another convergence zone that comes out at that time of year with a main peak somewhere around in April, called the Southern Intertropical Convergence Zone. Doing the same kind of thing for the rain rate, you can see, let me start over here. This is the signature of the Intertropical Convergence Zone and that Southern Intertropical Convergence Zone. Again, the Intertropical Convergence Zone being captured very nicely by those northern small boxes in the north. And then over on the west, the intertropical convergence zone is sort of moving across in southern hemisphere summer, and then back into the north in the rest of the year. So it's flip-flopping back and forth. A little bit of a overall view of the 10 years between that the quickscat was up, between 1999 and 2010, showing you the El Niños that were occurring, the darker shades here, and all the heavy rain during that period. And again, this is the West Pacific box. And in this year and this year, we had strong La Niñas, and you can see how a La Niña affects this West Pacific region. There's basically becomes a very dry area when the La Niña hits. And similarly for what goes on in the Central Pacific and the East Pacific. Okay, now what modifies the winds? Well, one of the things that modifies the winds are sea surface temperature fronts. So here's in the East Pacific some sea surface temperature pictures of sea surface temperature and sea surface temperature gradient, and you can see that there's a very strong SST front bordering the cold tongue, with these tropical instability waves show up here. And what happens? Okay, when air is flowing from cold to warm water, you're going from over cold, the air is nice and stable, and then when it goes over warm, you have convection overturning and mixing the air, so you're bringing faster moving air from aloft closer to the surface, and the slower moving air near the surface up in altitude. So that convective mixing has this kind of effect on the surface winds. As you approach that SST front, you're going from something slow to something fast, so you get some divergence. The rain also affects the winds. These in normal conditions,